So in this lecture we will be continuing with our discussion on the language Verilog. Now if you recall what we were discussing in the last lecture, we talked about the different logic values that the language Verilog supports. We talked about the primitive gates which are supported as part of the language. We looked at some of the hardware modeling issues, and finally we looked at some of the operators that you can use when we are describing a piece of hardware using Verilog. Now continuing with our discussion, today we start by stating or explaining some of the description styles which we may use in Verilog. See, the language Verilog supports some features, there are some instructions, some statements, some operators, we can use them, but you should also remember that there are several description styles which are available in the language. The same thing we can specify in possible different number of ways. Now, there are implications. The description style we choose, that may be differently interpreted by the simulator or by the synthesizer. So, it is necessary to know clearly what the different styles are and what they really mean. So, broadly speaking, there are two styles of description. One is the data flow description, other is the so called behavioral level description. Now, the main difference between these two is that in the data flow description we talk about continuous assignment, like you recall the assign statement that we had looked at in the examples we had given earlier. So, assign statement is an example where we are making a continuous assignment on a net type variable, and we had mentioned that this kind of style is typically suited for modeling combination logic, where the output of a gate may be driving continuously the input of another gate. Okay? There is nothing like clock or anything else involved. Now, in contrast, you can have another style of description, behavioral. This is more like you are expressing something in a high level language. You specify a set of statements which are supposed to be executed one by one, okay? But exactly how they are executed, that depends on whether you declare the assignments as blocking or non-blocking. This we will be discussing in some detail now. So, first let us again look at the continuous assignment data flow style. So, in the continuous assignment style, which you have already seen in the examples I have given earlier, this is specify using the keyword assign. These are some typical examples: assign A equal to B and C, or assign F2 equal to C0. Well, here the idea is that whatever you specify on the right hand side, for example, in this case there is an AND gate which will be synthesized B and C, which will be continuously driving a variable A. This A is not a register, this A has to be a net type variable. So, for a continuous assignment statement. So, essentially the assign keyword or the assign statement, it creates a static binding between whatever you are evaluating on the right hand side and the variable which you are assigning the value to on the left hand side. Now, the variable you are assigning to on the left hand side, this has to be a net type variable. I told you it cannot be a storage, because if it is storage it cannot be continuously driven, there has to be something like a clock. Okay. So, and one characteristic of continuous assignment is that it is continuously active. Now, continuously active means with respect to simulation, the value of the outputs does not change at particular points in time, like when there is a clock pulse. So, that whenever there is a change in the values of B and C, then after a delay equal to the delay of this gate, this output will immediately start changing. Okay.
So, what is your two continuous?
Yes.
Your two continuous things.
Okay. So, the question is that in say in a program, if there are two continuous assign statements, say assign say equal to B and C, say there is another assign D equal to say B or C.
No, A equal to B or C.
Oh, you are saying that the second assign is also
On the same variable.
on the same variable. Yes, this you can have. This I had mentioned earlier that this is a net type variable which is driven by two different gates. Now, it is your responsibility to ensure that A is either a wired or wired AND or a basically a wired type, because essentially this will mean that you are driving this net A from both these gates. Now unless you specify anything else, this will lead to a simulation error, or even this will lead to a modeling error. But if this A is declared as wired AND and wired OR, then there will be an explicit AND and OR gate synthesized out here. Or if these are tri-state gates, you can have tri-state controls. That is also permissible, right? Yes.
You have two continuous assign statements such as assign A equal to C,
Okay.
and then assign B equal to A.
Okay.
So all the three A, B, C will be wired.
You are saying if there is a statement assign A equal to B,
A equal to C is
A equal to B, and assign B equal to A, something like this,
okay,
or B equal to C,
assign C equal to A.
C equal to A. Well, now in this example, see, this different assign statement means they are all executed concurrently.
That's what I said.
Okay, so A and B have a correspondence, C and A are correspondence. So this A, B, C will be referring to the same net.
So the
Logically
new value
same.
of A will be stored in C, that is C will be equal to B.
Yes. So it is not that first this statement will be executed and then this statement will be executed. They are all executed together. So essentially, this synthesizer will be synthesizing as a single net, which may be referred as A, may be referred as B, may be referred as C. Same thing, right? Okay. So a Verilog module, whenever you are defining it, it can contain any number of continuous assignment statements, right? So as I had given the examples, and as I had said that the different assignment statements which are there using the assign keywords, they are all logically being executing in parallel concurrently. Okay, so there is no ordering of execution as such.
So whatever the new value comes in, it takes on the.
Yes, so whatever the new value comes in, it takes the net variable on the left hand side, it takes the value immediately. Now
After a delay, if there is a gate.
after a delay of the gate delay, of course, yes, and that net, if it appears on the right hand side of any other assignment statement, that will trigger the execution or the computation of that immediately. So this continuously goes on. So as I said, this is a natural way of modeling or representing typically combinational circuits, but we will see later that even using assign statements we can model a sequential circuit also, right? Okay. Now there are a few other things this I had mentioned, that an assign statement, say I have assign B equal to something, some expression. The first thing is that the expression, this can consist of any number of variables which can be of any type. They may be register data type, they may be net data type. So the sources of this assignment of this expression can be coming from any kind of variable, but when you are assigning it, this must be of net type. This is a restriction for continuous assignment statement. The left hand side has to be a net type variable, right? And like some of the examples we have already seen earlier. So now let us look at a few more examples that how this kind of assign statements can be used to synthesize some particular kind of, you can say, hardware blocks. Like this is a very simple example. This is a module which takes three parameters: data, select and out. Data is an 8-bit vector, select is a 3-bit vector, out is single bit. And here we give an assign statement out equal to data select. Now you understand one thing, right hand side contains a variable which is defined as a vector type, and the index we are accessing it with index, and the index is again a variable. This is not a constant. So if the index were a constant, like if it were something like this, out equal to data 2, then simply the bit number 2 of this data would have been directly connected to out. But since this is driven by a variable, this will be synthesized as a multiplexer. So, if you give this for synthesis, so this is data, the 8 bits of data. So, the 3 bits of select will come here, this is select and this will be out. So, the synthesizer is intelligent enough that whenever it encounters a, you can say, vector type register with more than one bit with a variable as the index, then automatically a multiplexer is realized, provided this appears on the right hand side of the expression. This is appearing on the right hand side of the assigned expression. So, as a result, a multiplexer is getting synthesized. But if this appears on the left hand side, yes.
The out is not declared as wire here, and by default it is a register.
By default it's a wire.
Out, if this is an assigned statement, this is taken as default as well, because I told you if you do not define anything, depending on the context you are using, some default is getting assigned. So, in this case, since you are using as the left hand side of an assign, it will be taken as a wire. But it is always good to explicitly declare all the variables, all the parameters you are defining, input, output both. That is a good practice. Well, this kind of a variable with a variable index, if it appears on the left hand side, like this example shows. In this example, the right hand side does not contain any expression as such, a single input data bit in, but the left hand side contains a variable with a variable index. Now, this will get synthesized into a decoder. There will be a single input in, there will be 4 outputs, these are the out, and there will be 2 select lines. Depending on what the value of select is, this in will be going to one of these 4. So, this is something you can just easily understand, and you can basically correlate that if such a thing appears on the left hand side, then in the synthesized hardware you can expect to see a decoder. If it appears on the right hand side, you can see a multiplexer. Okay. Now, there are ways to generate, you can say, a set of multiplexers or a vector of multiplexers. Like I am giving another example. Say this. A, B, F and select, these are the 4 parameters, where A and B are vectors of size 4, this F is also the same, and we are giving an assign using an implicit if statement, if select then A else B. So, effectively what we are saying is that, see, this A, B, F, these are all vectors of size 4. So, in this case what will happen, the synthesizer will be synthesizing 4 multiplexers, not 1. So, these multiplexers will all be 2 line to 1 line multiplexer, because this if is selecting 2 things, and out of these 2 things is selecting one of them. So, each of them will be having 2 inputs. So, basically this will be A0 and B0, A1, B1 and so on, A3 and B3. Similarly, the output will be F0, F1, F2 and F3, and all of them will be driven by the same select line SEL, all the 4. So, this single statement will represent a set of multiplexers, the number of which will depend on the size of the vectors. These are implicitly synthesized. Okay. So, now we shall show an example where even using assign statement we can synthesize a sequential logic. because this assign statement does not necessarily always imply that the logic you are generating will be combination in nature. See, the idea is that you will have to understand, or the synthesizer will have to understand, if there are any conditions where in which you may have to remember the last value of some variable. In that case, you will have to synthesize a latch or a flip flop. Just look at this simple example. This example models a level sensitive latch. So, what we are actually trying to model is that a latch with a input called D, an output called Q, and an enable En. So, every time En is high, this D will be latched. If it is low, it will remember the last value. So, inputs D and En are in, and an output is Q. You just look at this assign. Q will be equal to D if En equal to high, Q will be equal to Q if En equal to low. So, the same variable Q is appearing on the left as well as on the right hand side of an expression. Now, if this kind of a cycle exists in the assignment, this means that you are trying to remember something from the previous step. So, in a similar way, you can have not necessarily a single statement. Suppose you have a scenario where you are assigning A equal to something which depends on B, there is something else. There is another assign B equal to say C and something else. There is another assign C equal to A and something else. So, this means that you have a dependency. In the first statement, the value of B is used to compute A. In the second statement, the value of C is used to compute B, and in the third statement, the value of A is used to compute C. So, here also there is a cyclic dependency among these three variables. So, wherever you have this kind of cyclic dependency, you must have a latch, otherwise your logic evaluation will go wrong, right. So, essentially this case as well as the simpler example that I have shown, here the synthesizer will essentially check whether there is a cyclic dependency with respect to some variable on the assigned statements. So, if such a cycle is detected, this will automatically be translated into a latch in the synthesized hardware. Okay. Fine. So, these are the continuous assignment statements using assign. Okay. So, now let us look at the other style, the so called behavioral style. Now the behavioral style, which is sometimes also called procedural assignment statements or procedural assignment block. Such a block defines two things. First, just like any high level language, you write a program in any high level language, you can define a block of statements. Say in C you define a block of statement using the curly braces. So, similarly here also you define a region of code which will contain statements which are supposed to be executed one by one, right. So, just like a procedural language, a high level language like C, you have a region of code which contains sequential statements, and your understanding is when you are writing the code that the statements will be executed in the order they are written. But in terms of the hardware realization, you can understand that you cannot always necessarily guarantee this, that they will be executed strictly in the order they are written. There can be some parallelism also. Now, in fact, there are two different ways we will see that we can execute these statements. This will come a little later. Okay. But before that, let us do one thing, that the procedural block, whatever we are saying in Verilog, there are two types of such procedural block you can use. Okay, one we have already seen in a couple of examples earlier. You have a always block. This always block is a loop which never terminates. So, the idea is that whenever we have an always block, always you recall there is something like this, always at within parenthesis we have some triggering condition, pause h clock or some variables, then you have a block of statements in between. Now, this always block is like an infinite loop, it continuously goes on executing, and every time this event expression evaluates to true, this block gets executed once. This block never terminates, this goes on executing indefinitely. Statements, it depends again. I have told that there are a couple of alternatives. We will see this very shortly, that exactly how the statements are executed, but whatever they are sequentially or parallelly, whatever, they are executed every time this triggering expression holds true, and this is executed continuously in loop, this never stops. But in contrast, there is another kind of a procedural block called the initial block. This is executed only once, executed once at the beginning of simulation. See, there is something called a test bench. This initial block is used in a test bench. Now, let us try to see what is a test bench.
The initial block is not synthesizable.
Initial block is not synthesizable. The idea is that suppose you have written a Verilog code. This Verilog code can be written at the behavioral level also, at a high level. Then possibly you are using the synthesizer, you are carrying out synthesis to get a lower level description, maybe a get level netlist. This can also be a Verilog code, because after synthesis the synthesizer can also generate the synthesized netlist in terms of Verilog. Now, the problem is that after every translation it is always better to check whether this specification and whatever you have got, they are matching. This is done with respect to something which is called Verilog test bench. This is something which is again written in Verilog. Verilog test bench, what it does is that this is basically a Verilog program which is calling this Verilog module, and it is explicitly applying some input values to it, and it is checking what is the output. So, exactly during simulation whatever you are expected to do, that is done by the Verilog test bench. So, the same Verilog test bench may be exciting this code and evaluating the response, and also it can be exciting this code and evaluating the response. The same Verilog test bench program can be used once to check this and another time to check this, or to compare whether the outputs of the two are the same or not. Now, as you can see, Verilog test bench is something which is used only for the purpose of verification through simulation. This has to be executed only once when you are actually simulating. So, it is not that you are synthesizing a piece of hardware which has to be executed continuously, and in the Verilog test bench you have that initial block which is the analog of the always block, which is executed only once, right. And as you have correctly said, test bench is a program which is not synthesizable. You will see that you have statements which can read some data from a file, which can display some values on the screen. Those kind of statements can be included in this. Okay, fine, right. So, the initial block will come a little later when we talk about test benches. So, for the timing we start by looking at the always block only. Now, a module can contain any number of always blocks. There can be 4 always blocks, and the semantic says that all the 4 always blocks are executing concurrently. They will correspond to 4 different pieces of hardware which are executing without any interdependence. This is the basic syntax. This always blocks we have already seen. Always at the rate, there is something called an event expression. Now, every time this event expression evaluates to true, the block starts executing. The block is bounded by the begin and end keywords. Begin and end keywords will identify the boundary of the block, and there can be several statements in between. Now, this event expression, as we have seen in the example earlier, this we give both for modeling combination as well as sequential logic. For sequential logic, if there is an edge of the clock which is specified, pause edge clock or neg edge clock, that implicitly means that we are trying to synthesize a sequential logic. Or for combination logic, you can even say some combination of variables, always at A or B or C. If either A or B or C changes its value, you want to evaluate this block. But whether it will be synthesized into combinational or sequential, that depends on a number of other factors we will see shortly. Okay. Fine. So, this is the syntax of the always statements, and there are a few things. Now, in the always statements, you see this always statements is triggered by some event. Just try to understand, this is triggered by some event. So, you really do not know when the event will take place, and in the statements this will typically be some assignment statement, some expression is being evaluated, it is assigned to some variable. Suppose some value was assigned to a variable. Now, you really do not know when the next event expression will take place. So, till then you will have to remember or memorize the value. So, this implicitly means that the left hand side of those expressions of the statements, they cannot be a simple net type variable, they will have to be a register type variable, reg type variable.
That is why earlier you had said
yes,
in the always block on the left hand side.
Yeah, in the always block on the left hand side has to be reg type variables, because you really do not know when the condition will be evaluating to true. So, till then the value have to be retained to its old value. Okay. So,
Sir, when we say that the statements are concurrently running,
yes,
like in an assigned statement,
uh-huh.
in effect they become sequential because whenever one value changes, the other value changes after the delay. So, it's
See, there are a number of statements which are running concurrently, but they are sequential. Whatever you are saying is that there is a logical dependence between us. Say the output of an AND gate is driving the input of an OR gate, but in terms of the hardware, there is no one which is telling the OR gate that you please do not evaluate until the AND gate output becomes true. Now, just if you look at the simulation results, you will see that there will be a period of time when the output of the OR gate will be indeterminate. Finally, it will be settling to a stable value.
so isn't that sequential in the sense that everything is
Well, it is sequential at a lower level of granularity, where the sequential nature is driven by the delays of the gates, not by any clock or any external event.
So you said we can specify the delays. So if you make the delay 0, will there be some?
Well, you can specify the delays, but I also mentioned that the delays are meaningful only for the purpose of simulation, not for synthesis. So, when you are doing a simulation, if you specify some well defined delays, it will be easier for you to interpret the results. You can say that after 10 units of time this is supposed to change state. You look at the timing diagram and see that, well, yes, this after 10 units time there is some value which is changing.
And sir, if suppose an AND gate is driving an OR gate,
AND gate is driving an OR gate,
and we make the delay as 0, so the OR gate will take the changed value or the.
So, if you make the delay value as 0, then the simulation result can give some inconsistent values depending on the order these statements are appearing. They will be evaluated in that order.
Then it depends on operating system of the computer.
That depends on the Verilog simulator you are using, not really the computer, Verilog simulator you are using. This can vary from one simulator to another. Okay. Fine. Then the always statement, as I mentioned, so let me just again repeat this state, that only reg type variables can be assigned within an always block. This I have already given the justification, because this will execute only when the event expression triggers, and all other times the block is doing nothing, it is lying in the idle state. So, the variable you are assigning to must remember the last value. This is just what I just mentioned. So, in always block, the left hand side has to be a reg type variable, but however on the right hand side in the expression you can use any kind of variable, may appear in the event expression or also in the event expression. So, let us again go back to this one. So, in these statements, the right hand side of the statements as well as the event expression, you can have any combination of any kind of variables, net type, rich type, anything, but only in the left hand side of these statements they must be rich type. This is the restriction. Okay. So, before talking about concurrency within an always block, there are two alternatives out here, we will come to that. Before that, let us very quickly look at the different sequential statements that are there in Verilog. I mentioned that within an always block you can have several statements which are sequential one by one. Now, the sequential statements that are supported in Verilog are like this. First, of course, is the conventional begin end. Just within begin end you can have any number of statements, and just like C or any other language mostly used, that if there is a single statement in the block, begin end is optional, and you can have an if else kind of a thing, if expression then a block, else a block. Now, inside these blocks you can again have begin end if there are multiple statements, this else is optional. Then you can have case exactly like C, the syntax is very similar to C, case within bracket the case expression, these are the different values, this expression will be evaluated, if it matches this then execute this, there can be a number of such, and if it does not match with anything then a default, just like C. There are a couple of other kinds of statements which are not available in a language like C. For example, this represents an infinite loop, forever a block. This set of statements are supposed to be executed indefinitely, this you can have, and in this version you can say that I want to execute it so many times, I can say repeat 10, then some statements. This set of statements will be executed 10 times. So, if you want to execute them a fixed number of times, you can use the repeat statement. This while statement is exactly similar to what we have in C. There is an expression which is evaluated, and if it is true you execute this, otherwise next statement.
So, after repeat the set of statements you want to execute it 10 times, they have to
Yes.
do it in a begin end block.
So, after repeat the block of statements you want to repeat, say this all these statements I am saying sequential statement, this can be a macro statement, a begin end block, this can be a begin end block. If it is a single statement it can just lie as it is, but if it is a, if it consists more than one statement, this will lie in a begin end.
If there are two ifs or two whatever, again begin end.
Begin, yes. And this again this for expression is exactly the same as what we have in C. So, these are the different options you have when you write your code, and a couple of other things. This also we have seen in the examples that you can specify some time value using the hash, say hash 20, then you can give some assignment statement. This actually specifies a number which is a multiple of a basic time unit. This is, I am repeating, this is meaningful only to the simulator, and this specifies that the block of statement that follows, that block that follows, this can be a single statement, this can be a begin and again. This block has to be suspended for so many time units. So, after so many time units you execute this. So, in a sense you are specifying the delay of this block, that means how after how much time the output of this block will get evaluated. Okay. And at event expression, this I have already mentioned, this makes a block suspend until event expression becomes true or it triggers, whatever you say. Okay. So, now let us look at a few examples where we will see that how we can use this always block, for instance, to model different kinds of logic. First, let us take an example of a simple 2-line to 1-line multiplexer. There are 4 parameters. So, actually what we are trying to model is that there will be 2 inputs, in 0 and in 1, there will be one select line.
Sir, how do you know that it will be
Okay, so so you are asking that how do I know that that whether this will be synthesized into a combination logic or a sequential logic? Well, here we are trying to address exactly that question now. So let us look at a couple of examples. You will just understand how this decision, or means actually how does the synthesizer know that that exactly what to synthesize. Just to look at this example first. This says that you have in1 in0 SF. Well, since we are using inside the always block, this f I am declaring as a reg type variable. This always block, number one thing is that it does not contain any clock. Okay. So this does not directly imply that we will have to use a sequential logic, but you will have to see the internal of that block in order to finally conclude. Now let us see, this always block will trigger if any of the inputs change in 1 or in 0 or s. This says, the computation says that if s is 0, then we assign in 0 to f. If s is 1, you assign in 1 to f. See, you are taking a decision based on the value of s, and along all the paths of this decision process, you are assigning something to f. There is no path in this example at least where you are not assigning anything to f. So, that whatever is the value of s, something will get assigned to f. This implies you need not have to remember anything from the past. The current execution block,
We had seen there was only one if and there was no
yes,
else path.
yes, yes. If there is no else path, then you will have to remember the last value of f. So, if you have specified all possible paths and the corresponding values that need to be assigned to this f, you need not synthesize this into a sequential logic.
But
So,
there is a problem.
yes.
You have declared f as a register.
f as a register,
Now, as you told, countersign statement cannot put values to a register. You need to have a net. Like f is supposed to be net if you are using countersign. You are using combination logic.
yes, yes.
Since f is register, it has to put within an always block. It has to be sequential logic.
Now, number one thing, see, this f is a register does not mean that the logic you are realizing to assign to f has to be sequential. See, here we are synthesizing the logic that is used to generate the value of f.
But sir, it will synthesize a reg as some value, some hardware block that can store a data.
See, reg whenever you declare, then the synthesizer has an option, you can synthesize it as a register if required, or if you see that it does not require storage really, you can also map it into a wire.
Sort of optimization.
Some kind of optimization. So, reg does not always imply that you are generating a register. Okay, fine. So, this is an example where you are synthesizing a combination logic. Now, for sequential logic, we look at a couple of examples. First, you see that we have an example out here where we have a sequential logic, well, which is say just let me repeat once, say here you have an example out here. So, we are trying to synthesize a D flip flop in this case. The input will be D, you have a clock and you have both Q and Q bar. This is what we are trying to synthesize. Now in this case we are explicitly saying that always at the negative edge of the clock, so this will be a negative edge triggered. So, always at the negative edge of the clock you assign D to Q and D bar to Q bar. So, this is something which is triggered by the clock. So, implicitly this has to be a sequential logic because this is clock driven. So, everything, if in the always block there is a phrase where either neg edge or the pos edge of clock is used, this implies that you must have it realized or implemented as a sequential logic, because whatever assignments you are making, that will be done only when the clock edge comes. That can be done only if you have a sequential logic out there, right. Fine. Now, let us look at an interesting example. Say we have an example like this. This is some specification where you have two parameters to this module, current state and flag. Current state is a 2-bit vector, flag is also a 2-bit vector which is declared to be reg, because we will be using it at the on the left hand side inside always. Now, you have a always block out here. Just have a look at this always block. This always block checks the current state. Now, if the current state is 0 or 1, you assign some value 2 to flag. If it is 3, you assign 0 to flag. But in this case statement, you have a case. So, this case statement can potentially have 4 arms, because the current state can hold 4 values 0, 1, 2 and 3. But you are assigning the values only if it is 0, if it is 1 and if it is 3. But when the value is 2, this case statement does not take care of that condition. So, as per the semantic goes, the meaning of this means that if the value is 2, then the last value of flag should be retained, it should not be changed. So, this implies that flag has to be stored in a flip flop, okay. Flip flop or latch, whatever, it has to be stored in a storage element, because there are certain conditions under which you will have to remember or retain the old value of the flag. So, this is what the synthesizer looks at, whether inside the always block the variable you are assigning the value to, they get assigned a value for all possible branches. So, what I am meaning to say is that suppose you have an always block, your always block, you have begin end, there are several statements, there can be several if statements, case statements, whatever. So, in this block, if you do a code analysis, you can say that there are a number of possible paths of execution depending on the if then else. So, what the synthesizer will check, that it will check that whether along all the possible paths the values are getting assigned to the variables which are appearing on the left hand side out here. Say if f is the variable which is appearing on the left hand side, there has to be some kind of an f equal to assignment along all these possible paths. If such a thing is there, then only you can synthesize this as a combination logic, because you know that whatever condition or the inputs are coming, you know based on that input you can have some value of f. But there is no path where the value of f is unspecified. If it is unspecified, then we will have to map it into a sequential logic, right. So, just you look at the previous example once more, the value of 2 was not specified.
Sir, here that is why flag is to be used as a latch. In earlier case, since you have specified all the values, so it can be a wire also.
Yes, if I specified all the values, it can be a wire also, but since here I have not specified all the values, this flag can be a latch. But suppose as a designer, well, I understand that what I really mean is that if the current state is 2, that means I do not want to change the flag, or I want to set the flag to some value, say 0. Then actually how means exactly what do I do? Then I can make a small change to the previous code. This is one way I can handle, there are other ways also. I just add this one statement out here. Well, here I think I missed one thing, there will be a begin end, I missed the begin end statements. There will be a begin statement here, there will be an end statement here. Okay. So, here what it says, that is always statement, this always block consists of 2 statements, one is flag equal to 0 and the other is the case. Now, you see you are starting with by setting flag equal to 0, Then in the case statement you have a path where the current state is 0, where you are setting flag equal to 2. There is another path where state is 1, where again you are setting flag equal to 2. There is another path where the state is 3, where you are setting flag equal to 0. But what about the other path? See, other path also gets a value assigned to f, because at the beginning, irrespective of the current state, we are assigning some value to f. So, the only thing we need to check is that whatever path is followed, some value should be assigned to the variable along that path. Now, since we have already assigned something at the beginning, so the value by default is getting assigned for all possible conditions. So, this specification will be generating a combination logic. So, by this we are avoiding the latch. So, here we can either do this or you can add another case with 2, both are okay.
If this flag was outside the always block, then that would
If
not.
the flag was outside the always block, then it not be the case, because the always block is something which is going in an infinite loop. Right. So, every time the always block starts, you will have to check that.
Sir, if instead of current state we had a edge triggered something, then it would be a
Okay. Then what I have said earlier is that if in the always event expression there is an edge of a clock, then whatever is inside, irrespective of that, it will be a sequential logic. Yes. But if this is an expression based on only some values, there are no clocks involved, then you will have to check the inside to decide whether this can be mapped into combination or sequential.
But sir, for the simulator, how does it make a difference whether variable name is the current state or variable name is clock? Like material, whether you name the variable.
For this simulator it does not matter, but for the synthesizer it matters. See, this you can map it or synthesize it as a flip flop or not as a flip flop, not flip flop, a latch. Latch will be enabled continuously. But if you simulate, if you look at the value will be the same in both the cases. Maybe if you have a latch, the delay will be slightly more. That's all.
So what I am saying, like you said, like if it always at the rate some clock,
Huh.
then it's sequential. Always at some current state, then it's combination.
It can
How does it like?
For the simulator, it doesn't make a difference.
Like, even for the synthesizer, if I name my clock as some variable which I don't like to name my clock as a clock.
Name anything, but if I give that posage or negage,
Okay.
posage negage means I am triggering something at the edge of some variable. That has to be an edge triggered some operation. Okay.
the
Sir?
case,
Yes.
case statement has a break.
Case statement. Well, here I think I have not expressed the syntax in a proper way. Case statement can have a break after this, flag 2 break. Yeah, you are right. There will be a break here, just like C. Yeah.
In this example, in order to avoid the latch, you are in a way destroying the value of flag. By
We are
assigning
destroying the value of flag if it is okay with my specification, but
So, is it a good practice?
no, see, if my requirement, the design I am trying to do, if it is such that under the condition this state equal to 2, the value of flag I assign is a don't care thing, then I can afford to do this, but otherwise I should not do this. You are right. This is not a good practice. But if under certain condition it is really a don't care thing, then we can do the thing. Okay, so let us just look at a couple of other examples. This of course does not specify anything new. Here you have a 4-bit ALU specification. So, the ALU is such that you have two input operands A and B. These are vector, 4-bit vectors A and B. You have a function which is f. This f is also defined as a 4-bit, not f, sorry, f is the output, right? F is the output and op is the functions. Op is a 2-bit quantity. Now here, well, you recall I have said a parameter is a named constant. For readability of the code, it is always good to define the constants with some names. Like for example, I have defined the parameter 00 bit combination means add, 01 means sub, 10 mul, 11 div. and I can write the always block like this. Whenever any one of these three changes, case op, if op is add, do this, if is sub, do this, mul, diff. Now you see here this is a correct specification, but this is not a structural specification, this is a specification which I am doing at the behavioral level, because I am simply this adding, subtracting, multiplying, dividing two vectors. But if I want, I can specify at a slightly lower level. I can say that well, the addition has to be done using say a carry look ahead adder, or the multiplication has to be done using Booth's algorithm, say. So if I want to specify those, just instead of simply writing f equal to a star b, I will have to write a module for multiplication, and I will have to instantiate or call it here from here.
This is again combination because all of
This is a combination, yeah, the combination, because of all possible combinations we are specifying. So let us show another combination logic example. This is an example of a priority encoder. Priority encoder, here we have 4 inputs. This is in. We have 2 outputs. This is your code. And just to recall, what is a priority encoder? The priority encoder says there are 4 inputs. Normally the inputs are 0. Say the inputs are normally 0, 0, 0, 0. So the which input is 1, I will be encoding that into a 2-bit binary number. Now you look at this code, this always in, whenever in changes state, I will execute this block. Here I am giving a case statement. Case, well, the expression is a constant value 1, so I am comparing these with 1, and the order in which I am applying this is the order in which the check will be made. First you check if input 0 is 1, then you check input 1 is 1, 2 is 1 or 3 is 1. So the which one you encounter first, that code you generate. So the priority goes from this way, right. So just using a case statement like this, you can synthesize a priority encoder. Fine. So so in this lecture we had looked at number. Yeah.
The other way that input 0, input 1, input 2 are being compared to 1.
Okay. In this example, let us again come back to the example once. This input 0, 1, 2, 3, we are comparing it to 1. See, case statement what it does. Here we specify an expression. Expression gets evaluated, and the value of that expression is being compared with these values which I have specified. So I am specifying whether I am checking whether this is equal to 1, then this is equal to 1, this is equal to 1, or this is equal to 1. This is the order I am checking. That is the priority. That is the semantic of the case statement, that it has to be checked from top to bottom. There will be a break. There will be a break. I have not shown the break, because the check, the semantic of case says that it has to be checked from top to bottom. So the synthesizer will have to take care of that. That is why it will be synthesizing it as a priority encoder and not a conventional normal encoder. Okay, so in this lecture we have looked at some of the modeling styles, how we can model both combination and sequential logic using the always block. Now the one thing we haven't seen as yet, that what are the different kinds of assignments we can make inside an always block. This is something we will be looking at in the next class.